Hello, everybody. Welcome to today's lecture. Today we're going to talk about 8.2, which is very similar to 8.1. It pretty much just talks about how to do this with a different distribution, which normally I might skip over, but the distribution it introduces in this chapter is a new distribution that's really important in statistics, so I think it's worth going over. 8.3 does basically, again, the same thing. It just goes over the same thing with a different distribution, which is one that we already talked about, the binomial distribution. So I'm not going to go over that one. Pretty much everything is the same. It's just that because it uses a different distribution, the formulas look a little bit different, but the process is exactly the same. You just have to adjust the formulas for the type of distribution. So have a read, have a look at that one if you are curious, but I'm not going to require you to know that material. That one, it talks also about, here we're calculating the population mean. That one talks more about proportions. That's where the binomial distribution comes into play. So it might be worth looking over, but just in the interest of time, I'm going to just look at 8.2. And then after that, next time, we're going to move on to chapter 9, where we talk about hypothesis testing, which is very important because, we often want to know, how do we test our hypothesis? But anyway, coming back to this, now we're going to look at 8.2, which is titled, it's a long title, so I'll just read it. A single population mean using the student t distribution. Okay, so the student t distribution is the new distribution that I'm talking about here. Just as a reminder, let's just, Let me just, there we go. Look through the steps because they're going to be basically the same here. We wanted to calculate the sample mean, find the z-score, calculate the EBM, and then we make our confidence interval from that. So it's going to be similar here. Now, everything we did last time was dependent on knowing the population standard deviation. Okay. So last time we needed to know the population standard deviation. As you can probably imagine, in practice, that's extremely unlikely to happen, right? We typically can't do anything with the entire population because it's just too big, right? That's why we take our samples. So if we don't know anything about the population, it's hard for us to calculate population standard deviation. In fact, if we were able to do that, usually that means we probably would be able to calculate the population mean also. And if we can do that, then there was no reason to do the confidence interval in the first place, right? Because that's what we're trying to estimate. Or trying to figure out what the population mean is. So if the sample size is large, then it's fine because then we could just use the sample standard deviation and use it to approximate the population standard deviation, right? So if your sample size is large, the sample standard deviation would be a good estimate for the population standard deviation, and you're fine. Okay. But, oftentimes it's not the case. If the sample size is small, then you're going to get a confidence interval that's possibly wildly inaccurate. Okay. So the book goes on to tell this story about William S. Gossett. Okay. William S. Gossett, he worked in a brewery for Guinness, and he basically ran into this problem. He did math for them. He ran into this problem where he was working with very small sample sizes, but his predictions were wildly inaccurate, right? And for a big company like Guinness, that's you really need accurate predictions. So he came up with what's called the student's t distribution, which is basically a distribution that's used when your sample size is small. Okay. So small in this case we typically mean that the sample size is less than 30. Okay. If the sample size is more than 30, we can use the normal distribution. If sample size is less than 30, then we use this new one. Okay. So let's start writing this down here. By the way, William S. Gossett, he did this under the pen name student. And that's why it's called the student's t distribution. Okay. So the student's t distribution. Okay. And from this point on, we'll probably just call it the t distribution. Okay. Is used when the sample size is at most 30. Okay. For samples larger than 30, we use the normal distribution. Okay. Now again, we typically wouldn't know the population standard deviation. But the thing is, if the samples are larger than 30, then using the sample standard deviation instead of the population standard deviation creates results that are accurate enough, basically, with the normal distribution. But with sample sizes less than 30, if you're using the normal distribution and you replace the sample standard deviation with the or you use the sample standard deviation instead of the population standard deviation, then it becomes very inaccurate. So then that's why we have to use this different distribution. Okay. Now it also mentions this is typically how it was done, at least before computers. Now that we do have computers, so like this is basically like for calculations by hand. With computers, we use the t distribution anytime we replace sigma, the population standard deviation, with s, okay, the sample standard deviation. So anytime we replace sigma with s, we use the t distribution. Okay, so it doesn't actually, so nowadays it doesn't really matter what the sample size is. If you were just doing it by hand, like it mentions here, in the mid 1970s is kind of when the conversion was made over to computers. Once you started using computers, we just do this anytime because it's going to produce better results. Okay. So if we draw a sample of size n from a population with an approximately normal distribution. Okay. So this is just like last time. We were taking our sample from a population with an approximately normal distribution. really it's from a normal distribution, but we say approximately because it's not always going to be exactly a normal distribution, but it's usually in practice, it could be close enough, right? With mean mu, which is still unknown, right? Wait, hang on. Let me check one thing. Okay. Yeah, so the mean mu, which is still unknown. But now the difference between this one and the last one is now the population standard deviation is also unknown. Okay. Sorry, I just lost my place here. And unknown population standard deviation, sigma. Okay. And you calculate the t-score. Okay. So t-score is similar to the z-score, but it's going to look like this now. X bar minus mu over S over root n. Okay, so we have the population mean, the sample mean, the sample standard deviation, and then the sample size. Okay. Then the t-scores follow a student's t distribution. Okay. Student should be capitalized because that was a name. So this is similar to how the z-scores would follow a standard normal distribution. Now the t-scores will follow the student's t distribution. So remember the z-score, wherever we first had that, I think 6.1, yeah. The z-score was right here, x minus mu over sigma, okay? So this one is similar. It's now x bar minus mu over s over root n, okay? So instead of sigma on the bottom, we have s over root n, and instead of x here, we have x bar, okay? But it's a similar type of formula. So specifically, it's the student's t distribution with n minus 1 degrees of freedom. Okay. So this is something we haven't defined yet. I think the book defined it earlier, but so let's write a side note here. Degrees of freedom are the number of values in the final calculation that are free to vary. Okay. So the number of values in the final calculation that are free to vary. I just got that from Wikipedia. Okay. So the way the book explains it in this context is that when we calculate the sample standard deviation, we use n deviations from the mean. So that's going back to the way we calculated this all the way back in, I think it was 2.7 here. Like in this example, we had 10 deviations from the mean, and this is what we use to calculate the standard deviation. So because the sum of the deviations is 0, so if you add all of these up, you get 0. Then if we know n minus 1 of these, then we can figure out the last one. Okay, so that's where we're getting the degrees of freedom from. In this case, because we know these all add up to 0, if we know at least 9 of them, then we can find the 10th one. Okay, so that's how we figure out the degrees of freedom. In our case, with the t distribution, just because it's heavily based on the sample standard deviation, it is always going to have that n minus 1 degrees of freedom. So it's not something that we really need to think about too much. We don't really need to think about like what the degrees of freedom are. It's more so just going to be vital to us when we do the calculations using either a table or using Excel. It's always going to ask for the degrees of freedom. Okay. So we just have to remember that it's n minus 1 degrees of freedom. Okay. Which we typically would abbreviate as df. Okay. We'll see another distribution later if we get to that section called the chi-squared distribution, which also has degrees of freedom. So it's not unique to this one necessarily. Okay. So the graph for the student's t distribution is very similar. Let me pull it up actually. Okay, so I just pulled up the Wikipedia page here. You can see right here what the t distribution looks like. So you can see that the blue line here is the normal distribution, the red line is the t distribution, and the point it's trying to make is that as the degrees of freedom get bigger, it gets closer and closer to the normal distribution. Okay, so this is like 1 degree of freedom, whereas this one represents 30 degrees of freedom. It looks almost identical. Okay. There's another picture of it right here. So as the degrees of freedom, basically the larger number of degrees of freedom that we have, the more accurate it's going to be, which should make sense because the degrees of freedom comes from our sample size, right? So basically what we're saying is the larger the sample, the more accurate this is going to be, which of course it is, right? If we have a very small sample, it could be wildly inaccurate. Here's a picture of Gosset, by the way, just for curiosity's sake. The other thing I wanted to point out was that at the bottom of this page, there's another table here, which I'll show you guys how to use in a minute here. Or we can just do it in Excel, of course. So let's look at what is different here. Okay. So the notation for the t distribution using t as the random variable, normally we use x, but they're just using t here because it's the t distribution. You could just as well use x though. T is distributed as a t distribution with however many degrees of freedom, where df equals n minus 1. So sometimes you might just see this written as t n minus 1. Okay. In fact, it's probably on this Wikipedia page somewhere. I don't see it off the. Yeah, I don't see it. So I won't spend a lot of time on that, but I'm sure it's on there somewhere, this notation as well. So if we have 20 items, for example, then T would be distributed as a T distribution with 19 degrees of freedom. Okay. It's always one less than the sample size. So in this case, our EBM is going to be different. Okay, so the confidence interval is going to be the same idea. We need to have the sample mean minus the EBM, the sample mean plus the EBM, just like last time, but the EBM is calculated differently. The EBM is equal to our t-score. So just like before we had our z-score alpha 2, this is the t-score alpha over 2 times s over root n. Okay. If you recall, the EBM before was the z-score times sigma over root n. So this is the t-score times s over root n. Okay. So we're replacing sigma with s, and we're replacing the z-score with the t-score. Okay. So the alpha is calculated the same way. We're going to have 1 minus the confidence level. Okay. So let's say let's do this example here so that we can see how to calculate the t-score and everything. If we look at example 8.8 here, it basically, 8.8, it asks us to construct a 95% confidence interval. We have 15 subjects. Okay. Let me just read out the whole problem here. Suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for 15 subjects with the results given. Use the sample data to construct a 95% confidence interval for the mean sensory rate for the population, which is assumed to be normal, from which you took the data. Okay. And here is our data. Okay. 8.6, 9.4, 7.9, 6.8, 8.3, 7.3, 9.2, 9.6, 8.7, 11.4, 10.3, 5.4, 8.1, 5.5, 6.9. Okay. Okay, so what do we need here? Well, if we're finding the confidence interval, okay, our confidence interval is x bar minus the EBM, comma x bar plus the EBM. Okay, so we need x bar, first of all, which we can calculate easily from these numbers, and we need the EBM. So we're going to need the sample standard deviation, and we're going to need our t-value. First of all, alpha is 1 minus 0.95 because this is a 95% confidence interval, so it's 0.05. So we're looking for t 0.025, right? So this is just like before, where you have in the t distribution in the tails, you'd have 5% of the data left over in the non shaded region. And so in each tail, you'd have 2.5%. And we're just looking at one of the tails. Okay. Let's go ahead and throw this data into Excel here. Okay. So that we can just have it do all of our calculations for us. 7.9. All right, so here's all of our data. You can see we have 15 of them. So we want the sample mean, and we want the sample standard deviation. So let's calculate those with our formulas here. Need to make this a little bit bigger so that the formulas show up. There we go. So we're going to do the average for the sample mean. We want these numbers. There's the sample mean, 8.22. And then we want the sample standard deviation. So remember, we're doing standard deviation point S. So we get 1.67 2238. Okay. Now, let's look at how we find the t-score. Let me get that pulled up. Okay, so I just brought that Wikipedia table back up here. So one thing I realized we didn't say was, remember, the degrees of freedom is 14 because we had 15 subjects. So it's one less than this. So, the book doesn't really write it like this, but sometimes you might see it written like 0.025 comma 14, because we really need both of these numbers to calculate what the t-score is, because it's going to be, we have to know what the degrees of freedom is, and we also need to know what the area of the region is, which is what the 0.025 is. So you really need both of these, which the book never really mentions. But you can see right here on Wikipedia, for example, it has T alpha n minus 1, because you really need both of these. So we need 0.025 and 14. So on the left side, this is listing the degrees of freedom. So we're going to 14 right here. And then we're looking for, on this part, you notice that there's a one-sided and a two-sided. Basically, the one-sided is the area for one side. So that would be the, this is the left side specifically, since we have 2.5% on the right side. It would be 97.5% on the left side. So we're on this column for one-sided. Two-sided is, okay, what if you just have both of them? So you don't do alpha divided by 2, right? So you just have alpha. So it would be 5% on the right side, 95% on the left side. So you can look for either one here. So you don't necessarily even have to divide it by 2 if you're using this table. But either way, you can find it. Okay. So we're in this column because of the 0.025. So the left of it is 97.5. And then we're going down to 14 degrees of freedom. So we line up right here. 2.145. Okay. 2.145. Okay. So now for our EBM, we need to do 2.145 times the sample standard deviation, which was 1.672, divided by the square root of 15. Okay. We can just do it in Excel. We can do 2.145 times the sample standard deviation. It's actually listed in C6, so we can just write C6 divided by, I don't know how to do square root. I'm going to guess, there you go, SQRT. Whoops. All right, let's see if this works. Let's say SQRT, yep, 15. Okay. Then we got to close that parentheses. So we get 0.926. Okay. It's a little different from the answer in the book because they only use 2.14 here instead of 2.145. So the CI confidence interval is X bar, which is this here. We can actually just do it right here. We need to do X bar, which is C3 minus the EBM, which is C16, right? And C3 plus C16, X bar plus the EBM. So there we go. It's 7.30 to 9.15. Okay. And that specifically is the 95% confidence interval, I should say. Okay, so you can see the process, it works pretty much the same as it did last time. It's just that the formula is a little bit differently. We have to calculate this sample standard deviation by hand, which is something we can just do in Excel. It's not given to us like sigma was in the last one. And then we have to look for the t-score, which the only difference here is that we just have to use a different table, essentially. Okay, let's do one more example here. Let's do example 8.9. Okay. So this one says a random sample of statistics students were asked to estimate the total number of hours they spend watching television in an average week. The responses are recorded in this table. Use the sample data to construct a 98% confidence interval for the mean number of hours statistics students will spend watching television in 1 week. Okay. So we'll move down here. I'll just put the table exactly how they have it written in this order. I'll just put it right into Excel. Okay, 5, 10, 1, 10, 4. Okay, so this is the table that they have. So we can see that there are 15, again, students asked. Okay. So we're going to need the sample mean again. We're going to need the sample standard deviation again. We're going to need to calculate the EBM again. Okay. So first the sample mean, again, we go to average, highlight the data that we want. We get 6.133. Sample standard deviation. Go to standard dev.s, and then we get 5.514. Okay. So we'll use those when we calculate the EBM. First, let's look at our t-value. Right. Alpha is 1 minus 0.98. So 0.02, right? So again, you can just use, like when you're looking at this table, you really can just use what the confidence interval is. You don't even really need to calculate alpha with this table specifically, because if you're doing a two-sided one, the two-sided value here is just telling you how much. It's just telling you the confidence interval exactly. Okay. Like when we did the 95% and we did it back to 0.025, it was just kind of a roundabout way of doing it. It was more relevant with the Z table, but here it's not really so important. You can really just look for the 98%. But just for the sake of using the book's notation here, we're doing 0.02 divided by 2, which would be 0.01, right? And the degrees of freedom, again, are 14, right? DF is equal to 15 minus 1, which is 14. Because we have 15 people, so we subtract 1 from that. So our EBM, well, first of all, our t-score here, what is it? Well, we're going to go to the 98% for the two-sided or 99% for the one-sided, and we're going to look for 14. which is right here, 2.624. Okay. So the EBM is 2.624 times the sample standard deviation over square root of 15. Okay. So this is going to be 2.6, what was it, 24? Whoops. 2.624 times the sample standard deviation, which is in cell, what is that? D33. Whoops. D33 divided by the square root of 15. So we get 3.74. We round it. Okay. So our 98% confidence interval is going to be x bar minus this, x bar plus this. X bar is 6.133. So we can go D31 minus D35. Whoops, 35. And D31 plus D35. Okay, 2.397 to 9.869. So this would be our confidence interval, our 98% confidence interval. Okay. And just as a reminder, this means that 98% of the time, based on this test, the 98% of these intervals will contain the actual population mean. Okay. And if we look at our data, it is a pretty big range, but it's because we have some outliers here like 20 and 14. Not technically outliers, but just like big numbers like that. So it doesn't narrow it down a whole lot, but that's because we're very confident in it with 98%. Okay, so we just got to find the t-score and then use the sample standard deviation instead of the population standard deviation. But other than that, it's pretty much the same as the last section. Okay. All right, so again, 8.3 again is pretty similar. It's just doing it with the binomial distribution instead. So we're going to skip over that. So next time we're going to look at chapter 9, which is hypothesis testing. Maybe the most important chapter we'll do, either that or linear regression, which is chapter 12. Hypothesis testing is basically, okay, if I want to test this hypothesis, what do I do? How do I know when to accept the hypothesis? How do I know when to reject the hypothesis? That kind of stuff. So very important stuff. We'll talk about that next time. And thank you for watching today, and I will see you then.